All right, so reinforcement learning, planning, and optimizations. Um, Leora and I do research here at UCF with UCF and the Air Force Research Laboratory, and uh, we do a lot of research in planning and reinforcement learning. AlphaGo Zero is one of the most well-known recent reinforcement learning like feats. There is an MCTS like algorithm, and MCTS stands for Monte Carlo tree search. We're going to talk about that more later. Um, but this allows you to look ahead, look into the environment. So, see if we had a rat um, in this maze, has to plan how to get to the end while getting that piece of pizza. So, oh, hello, Pedro. How you doing? Welcome to our presentation.
Glad to be here.
Yep. So we're talking about what does planning maybe mean in a reinforcement learning context. Does anybody kind of want to butt in and have any thoughts on that? We could kind of discuss before we get into things.
Um, Maybe it has some sort of foresight, or it's thinking about future steps, possibly.
Right. Yeah, there's definitely some look ahead, thinking to future steps. It's not just responding to, or it is responding to one state at a time, but it responds to that state and maybe models what future states could look like, kind of plans ahead. And we'll go into what that means kind of more in the reinforcement learning context. Take my jacket off. So I'm Brett Bissey. I'm a machine learning intern, and I'm a senior computer science major and stat minor. My research involves reinforcement learning and planning. I work with single agent as well as multi-agent environments. I mostly work with discrete action spaces, grid worlds, card games, board games. A lot of reinforcement learning is continuous action space, like, or, you know, different than kind of these discretized games. I don't have as much experience with those, but those are, just as interesting and just as relevant. And I kind of mentioned MCTS. That is the main algorithm that we've kind of worked with and published a paper kind of optimizing, and that's kind of what we're going to talk about today. Proximal policy optimization is another interesting, it's just kind of a different way to train your network when you're dealing with reinforcement learning. DQNs and neural fictitious self-play. And that self-play part of the acronym, it has to do with this planning as well. It's that's typically used in card games like poker. And the self-play aspect allows an agent to kind of look ahead before a move, play with themselves. I also do some research in adversarial computer vision model attacks. So this is like if you have an image and you want to see, you know how it's classified in a model, and you want to try to trick that model into classifying it a different way. It's kind of an interesting field of machine learning, and yeah, I mean, I'd love to talk about this after if you have any questions about how to get into research or these specific topics. So, planning and reinforcement learning, it oftentimes requires a model-based approach, and I kind of mentioned this earlier. A model-based approach means that we are our agent sees a state of the environment, and then it kind of models the environment and looks ahead in that modeled environment to try to plan. A model-free approach would see a state and make a decision instantaneously without planning ahead. But that decision could potentially be a better decision than planning ahead if you have a model, if you're model-free approach is trained well enough. So there's look ahead in the model environment based on the current state. Modern implementations use value approximations to reduce planning time. So this means that within our modeled environment, within the kind of search through the different game states within that modeled environment, we don't have to search every state to completion of the game, because we can kind of like approximate how good a certain state is with a deep neural network. And this is kind of how neural nets have encouraged growth in these areas of reinforcement learning. Like Monte Carlo tree search is a pretty old algorithm, but it's too time consuming, and it's not scalable to like general reinforcement learning. But if you can approximate states within this tree search, you can really reduce your time. So if you look at this, you guys have probably already started looking at this graphic. If you start, we'll start at the experience. Let's actually start at the acting. So this is your agent, and it acts, and it does an action, and there's an experience. And if you had a direct reinforcement learning, you would get a value policy straight from that experience, and it would continue acting, and it would just kind of go in that loop on the right side with the orange arrow. But if you had a planning-based approach, a model-based approach, after that experience, you would build out your model, you would plan based on that model, and your value would be coming from that model rather than the direct reinforcement learning route. So this is kind of an interesting graphic I found on the internet that compares both approaches. If you look at the time, it's 5:45. The model-based approach would be checking the traffic on your phone. The model-free approach would just be knowing that at 5:45 you don't take the highway. So, one is much more data efficient. You don't have to build out this whole plan of this traffic and what's going to happen, whereas the other could be more accurate but more costly. And with Monte Carlo tree search and these planning algorithms, run to completion, they could be 100% correct, because you could just look ahead and figure out every possible game state and every possible value that every possible like reward that you're going to get, and figure out the best move, kind of like doing this what's it called, brute force approach. But in reinforcement learning, we're looking for a more generalized model, one that kind of mixes this planning with some approximation to find the general approach. So within the game of Go, and this is a really interesting game for reinforcement learning, and it's what AlphaGo Zero is famous for. We see a state on the board. We have a 19 by 19 board with black and white tiles on it. It's a very simple state. It's a 3-layer tensor. We see this state, and during a play step, then we start building out a tree of possible other states that state could branch to. If we're going down the tree, we go by a heuristic, or like there's like a curiosity heuristic, there's a value heuristic. Like these different heuristics can guide us down the tree depending on like how we tune our hyperparameters, but mostly based on just like good traces that we've seen before in the tree. Once we reach a state that we haven't seen before, it's a leaf state, and we want to expand that leaf state. And we want to get a value from that leaf state. Now, in typical Monte Carlo tree search, we would run that leaf state to completion and assign a value to that node. But in modern implementations, that default policy will represent a call to the neural network. So once we get the value of how good one state in the game might be, what reward we might get from it, we backpropagate that back up through this tree, through the game tree. And so all these nodes, and they get like a discounted reward. So if you're at this final node, you might get a 0.99 reward. If you're at this second node, you might get a 0.75 reward. And you kind of scale this back, and each node like dynamically updates how a certain state might be. So once we backpropagate that information up, we use that information to choose our next state. And once we take that step, that place step outside of the tree, we save that data. We save our entire trace as state, action, next state, reward tuples or objects. And we're going to train on that later to train that neural network that we use within the net. And that's what that line represents. So it's this kind of like cyclical, we're using the neural net to help us make these play steps, and then the play steps are simultaneously training the neural network. So it's kind of like the neural network is helping us secondarily. A lot of you don't have to read through all this. I know it's a big no-no to put all these words up on the slide, but how our research kind of varies from typical AlphaGo Zero's Monte Carlo tree search is we're bringing in automaton through finite temporal logic to kind of represent environments and represent the games on grid worlds. And these automaton are going to help us with these heuristics in the Monte Carlo tree search to give us another heuristic based on how satisfied or what state are we of this automaton. And so if you guys have taken discrete, this is probably somewhat familiar to you. We have these state machines, just like DFA, and we have these different atomic propositions. And on this one, for instance, we have hostile and safe, and they're representing different states that, say, our reinforcement learning agent could be in. And given a formula, this LTL, linear temporal logic formula, says G means to always be. So wants to always be in a hostile state until it is eventually in a safe state. So you could imagine how you could kind of nest these equations and create like a game sort of, and that's what we did with grid worlds. So important questions of our research is how do we introduce an automaton guided reward shaping function within Monte Carlo tree search in order to increase data efficiency? How can we leverage state abstractions and formal verification techniques to train on explainable control policies? And can automaton guided reward shaping encourage emergent cooperative or competitive behavior in a multi-agent setting? I am going to, if anybody has questions of their own, I know I kind of went through everything really quickly. We do have some, this is kind of like the halfway point. If anybody has like questions about MCTS or anything on this page, feel free.
So you said that we could use different heuristics together. Like, can you explain more like what like a heuristic is? Like how many can we have? Like what that is?
Yeah. So this might make more sense when I start bringing in the automaton heuristic, but basically each of these nodes in a game tree it builds up statistics that represent the history of rewards traveling through that node. One statistic might be how many times has it traveled through this node. Another might be what's the average reward traveling through this node. Another may be like, we might have a curiosity heuristic. So if something hasn't been traveled to very much, or something has already been traveled to, we don't travel to it in like 5% of the time or something, to encourage like us expanding the breadth of our game tree. But yeah, we're gonna kind of go into more specifically what that means. But does that kind of help you?
Yeah, that makes more sense. Thank you.
Okay. Okay. So with these questions in mind, we're going to go forward into kind of the new part of the novel part of the lecture. So automaton guided planning. This is where we bring our DFA in. We have some high level objective. It's special instructions, and it's formalized into a state machine. And I believe this is actually one of the state machines for one of the grid world environments we had. And this has 7 states, many more transitions. And we're going to use like the transitions within this research to add a new heuristic. So we have our agent environment model. They both come together in MCTS, and we get an explainable control policy satisfying the objective. Part of the reason that DFAs are interesting in this context is because of like the explainable aspect. If you have something that says the agent is going to pick up 2 pieces of wood, then take them to the factory, and then take them to the home space, that is like, you can explain how the agent is training. Whereas in typical reinforcement learning and planning, you kind of have to do the explaining afterwards, and you kind of have to like, it's kind of more up to the algorithm and more up to like the model to figure out an optimal policy, and you have no way of kind of prodding it in different directions. This can also be like a bad thing if you don't have a good high level objective, because you could like hurt your model. You could potentially like you could be only looking at one way to like solve the objective, depending on how you formulate that. Okay, so learners will simultaneously reason about both a state representation, that is like this grid world, this environment with trees and a home and a factory. They'll simultaneously reason about both that and some objective representation. And this means these atomic propositions, if you can see, it's no small text, wood, tools, factory, build. So these are like logical operators that represent stuff that's happening in the environment. So wood might mean agent has wood, and you see the automaton is labeled with how it's going to change to different states based on these logical operators based on the environment. So this subjective representation is like a key part of how we're going to learn, because it kind of models our rewards, our intermediate rewards, before we reach that final objective, which would be to get 2 pieces of wood, go to the factory, and then go home. We're kind of modeling the in-between, or we're giving our agent a way to plan ahead to do those steps. Whereas in typical planning, we would just give it the final objective. We would say, you need to do all of these things. You would give that to the model, and it would end up learning how to get 2 pieces of wood, make a tool at the factory, and be at the home space, but it wouldn't be like a guided as using a DFA. And you don't see as good of rewards. And we'll go into the kind of these the experimental results from this as well. And I know that this is it's a workshop. We're gonna have like a little tutorial at the end if you guys want to do that. But I was gonna start with just kind of going through this research. So this automaton guided tree search is gonna go into how this automaton state heuristic is used within this research. So we have our selection state. This is the argmax function is basically it's taking it's looking at all of the action space. It's represented by this big A given a state, and it's finding which action is going to maximize this heuristic. And the Q is our estimated value. The Y represents our estimated, the Q represents our estimated value given a state. Oh. The U represents our how many times we've been there. And the Y represents our estimated value given the state of the automaton. So that Y is where the automaton comes in. So say we moved from state 0 to state 1, like in this diagram. And we pick up a wood at state 1. Not only are we looking at this entire state when we make this heuristic, we're also looking at the state of the automaton, which is when we travel from 0 to 1 at the top right of your screen when we grab that wood. So we're kind of taking into account this abstract representation of the space as well as this other kind of physical environment-based representation. As we expand the neural network, we're using our CNN to get our action probabilities as well as a value. It's a 2-headed CNN, so we have one head that deals with the probabilities of the next action and the other head that deals with the value. And we can get it's relatively, it's like an actor critic architecture, and you need both of these heads. Oh, backwards. Okay, so during the update, this is after we've made our when we're doing our backpropagation, we like update all these values, and it's just kind of a lot of math, but this is like how each of the heuristics is updating on a backpropagation, I believe. And this is just, I don't want to go over this too much because I'll probably mess something up. But these slides kind of show you how we're simultaneously tracing through this tree as well as the automaton. Lior.
Oh yeah, I have a question.
Mm-hmm.
Can you use an automaton in a free model where the heuristics are not combined during planning?
Yes, you could. But you would have to be keeping track of these automaton statistics in some other sort of model. So if you're using the model free approach, it might not technically be model free if you're also doing the automaton, but I think basically if you would keep track of the states in a certain trace, and then you keep track of the automaton states within those states and kind of like save those within nodes that aren't a game tree and use those during your model free. But it would still require kind of keeping track of these states.
I see.
Mm-hmm.
Okay, cool.
You could also potentially train another network. I hadn't really thought about this on like the automaton states as you're training, and you have like your automaton expected value, expected state, and another network that gives you your normal expected value.
Oh, and you can mix those together.
Mm-hmm.
Nice.
Okay, so this is kind of just showing how we're doing this entire tree search to figure out our play policy, and then we're moving to the next play step. And this play policy we have, it basically has to do with how many times have you done this state, done this action in this state, over how many times have you done the sum of all the other times you've done other actions in this state. So it's kind of like just wanted how that play step selection works. And then we're saving the play steps in our replay buffer, which we're going to train the network later on. So here's an example called the blind Craftsman. And this LTL objective in English says always get a wood and eventually go to the factory. Can you guys see my mouse?
Yes.
Yes.
Yes, we can.
Okay. Always get a wood and eventually go to the factory. And eventually have 3 tools and build a home. So there are a good amount of states, and this would require the agent to pick up a wood, go to the factory, build a tool, go and pick up another wood, go to the factory and build a tool, and eventually go to the home space. So it's like, it's kind of nesting that you have to do this first part 3 times because you need 3 tools to build the home. So it's kind of a complex planning situation that a typical algorithm might struggle with. And even MCTS might not be able to handle it super well because it has these labeled parts. And what we found with evaluating this, the automaton curve is using MCTS with this automaton statistic. The no automaton curve is using MCTS without the automaton heuristic being built up. And we see a quicker convergence and like a pretty large delta in that training early on. And this was, we also evaluated 2 other environments in the single agent case, actually 3 other environments, as well as some multi-agent evaluations, but the multi-agent is a bit hairy and I don't like explaining it as much. But yeah, this one, it really helped training early on to have this planning, this way of planning ahead. One interesting application of this is the transfer learning aspect. So because we have this like abstract objective space where we're describing like what's going to happen based on the automaton space that we're at, or the automaton state that we're at, we can transfer this to larger grids and larger game boards that also have other labels. They could be like we train on a 10 by 10 board, we transfer it to a 25 by 25 board. And it has like similar labels, but there are also mountains. And we use the statistics that we built up from the automaton in the 10 by 10 training, and we transfer those to our 25 by 25 training to kind of help within that tree search. And we find that it really helps. And transfer learning is kind of like the first step to a generalized reinforcement learning method. If you can train an algorithm on one environment and then it does well in another similar but different environment, it's a good thing. So this is these transfer learning results. So this is like after training on the 10 by 10 environment. The green is when we transfer those objectives, and we see a much a higher convergence rate on transfer. And the automaton without transfer still performs better than our no automaton MCTS. And this is on a 25 by 25 grid, very similar to that one. And then this one on the right is when we're using like randomized environments rather than fixed environments. Oh, and all these curves are like averages together of I believe, 25 training runs. So like randomizing your environment is also, it would mean like these mountains would like show up in different places on the environment, depending on different game steps. So you would kind of like be generalizing your grid space as you're training. And that helps robustness of a learning algorithm too. I found these when I was making this, and I thought they were kind of interesting. Just kind of how reinforcement learning can be used in all these different areas, and I've only really explored the games aspect of it. I'm only just playing these games. But there's so many areas where it can be used, specifically like transportation with some of the, like I feel like planning ahead and in tandem with direct reinforcement learning, could really change the way that we look at self-driving cars, and multi-agent systems has a lot to do with this transportation aspect too. But there are just so many areas where reinforcement learning is being applied today, and like it's really kind of a young field with lots of unknowns to research. And just as machine learning, it's like it's like an art, and there's so many different ways that you could like design these algorithms. And like our approach is just kind of adding this automaton onto another algorithm that somebody else made. So it's like, people are constantly building on top of each other's work, and just a fun, exciting field. So now we're gonna, if you'd like to, like, does anybody have any other questions? Or I can kind of.
For that mountain with the house grid world, what's the overall? Is there an overall goal?
Yeah, so the goal would be the same as the goal that we trained on, which was to, in the smaller space, which is to grab 2 pieces of wood, which would mean like go to the wood space twice, take those to the factory, which is the barn, I guess in this instance, build a tool, eventually have 3 tools, and go to the home space.
And so is the goal simply to complete that task, or to do it in some kind of like the shortest way or fastest way possible?
Yeah, so the goal is to complete the task. The shortness will come with time, with training. But yeah, so the goal is the same on both. Yeah, like as you train, your runs will get shorter if you have a good algorithm, because it will be learning like the algorithm is set up to coax out this optimal policy. My cat just jumped on the.
That's a nice cat.
Yeah, he's nice. Excuse me. So I do have a workshop, like a quick notebook I found. I did not author it myself, but it kind of goes over Q learning, which is direct reinforcement learning. And I'll share that in the chat for anybody that would want to check it out. And I'm going to share my screen as I go through that. Share screen. Okay. So Frozen Lake is similar to our grid world environment that we kind of just went over. There are the snowflakes, which represent spaces of ice, the holes, which represent holes in the ice, and the home space. The reason that Frozen Lake is kind of a benchmark environment is because it implements an icy, it's like an icy environment, which means you won't always move in the direction that you intend. Stochastic environments are like a way to add robustness to your model, because it kind of like it sits in for a way. It's like a randomization from the environment. So it's not always like a deterministic, if you make this move, it's going to be good. So you have to kind of like explore many policies. And this is coming from this dude's like course, and he has a good amount of stuff just kind of freely available. He has one with Sonic where it's like if you download Sonic, he shows you how to hook it up to an algorithm. So installing Numpy and Gym. This demo doesn't actually use any neural networks. It uses Numpy to keep track of a Q matrix, and the Q values are like the expected reward values. So it's going to keep track of a matrix at each space on the Frozen Lake grid. So we're going to import our dependencies. Let's make the environment. I know I'm just kind of clicking through this, and I would typically like write it out, but I'm just clicking through it. Our action size, because Gym is like a commonly used wrapper for reinforcement learning environments. So you can make a lot of the benchmark environments using Gym. And let me go in on that. It's probably a bit better. So each environment that's made using Gym will have an action space parameter. It'll have an observation space parameter. And like these will have their own, like the N is like how many actions are in the action space. Observation space. Let's see what. And our action size, I think it's going to be 4. Yeah. Yeah, so like the observation space is saying there's 16 discrete spaces that you can be at, and that's like a 4x4 grid. So it's 16 discrete places you can be at. you're moving to those spaces like up, down, left, right. Those are your 4 actions. And we're going to create our Q table. And this is kind of like a classic Q learning technique. You can do this without neural networks on a lot of grids, but this is a direct, it's not a planning algorithm. But this game would probably benefit from a planning algorithm. So this is a 4 by 16 grid. 4, yeah. With state size and action size columns. Okay. State size rows and action size columns. So for each state, when there's 16 possible states, right? That we're going to get Q values for the action at each state. And those Q values represent like how good that action will be, the potential rewards it may lead to. So these are all hyperparameters, and if you did this on your own, you can like tweak these and maybe even improve the reward or the learning rate. But in this case, the total episodes is like how many episodes you want to train for. The learning rate is a very important heuristic in reinforcement learning. There are optimizers as there are in other computer vision, like classification problems. There are optimizers that will adjust to like the learning rate that you need for your net, like Atom and whatnot. But with reinforcement learning, it's like the learning rate seems to be a very important heuristic, depending on the game, depending on like how hard the game is and all that. Max steps is we're only going to allow 99 actions per game, and then we're going to stop the game. The discounting rate is like if you have one trace through the grid, like one state after the other, you're going to discount the reward back through that trace. So if like you go down this trace, you discount it back up but each state you go back up, you like multiply by 95%. And that like scales your reward throughout. Exploration parameters. It's kind of what I mentioned earlier. You can kind of go to different states depending on if it's early on in your training or not. The exploration rate in this case is set to decay as you get later on in the game. So at the beginning of the game, it's like explore any action you want. But near the end of the game, it's like we're only going to use the learned policy. So in this case, at the beginning of the game, like the first step, you don't have to look at the Q table at all. It just says random policy. But the last step, you only look at the Q table and there's no sense of exploration. And in the middle, you kind of like, you start using the Q table more and more, and the randomness less and less as you get to the end of the game. So here's the Q learning algorithm. We're initializing, we already did that. Initialized our state action pairs, matrix for life or until learning is stopped. We choose an action in the current world based on our Q value. We take the action and observe the next state and the reward. And then based on the next state and the reward, we update the Q value at that state action pair. A lot of times there's like a lot of really like awful looking equations like this in reinforcement learning, but you can kind of just like try to figure it out semantically and gloss it over. List of rewards. So we're keeping track of our rewards, I guess. So for episode and total episodes, this is like 2,000 episodes. We reset the state at the beginning. We set done to false. And this is very similar for most reinforcement learning training loops. They're going to look very similar to this, no matter what environment you're doing. So we choose an action. This is our exploration exploitation trade-off is what that means there. And that is, how much are we exploring? How much are we exploiting the policy? And that's like what's decaying throughout each of these each game. So yeah, so then we're taking the max action based on the Q value at a particular state. So like we plug the state into our Q table, and then we pick the max Q value from that. George, how you doing?
For the exploration rate, would it make sense to decay it based on the current win rate approximation instead of decay linearly? Like it's going down by, in this example, it's going down by like 0.005 after each step, right?
Yes.
So would it make sense to, instead of doing that, decay it by the current win rate? So if like the win rate is 50%, then you should explore 50% of the time.
Yeah, that actually does make sense. You would need like an outer layer of this that checked the win rate and like changed that decay rate, that decay rate would be like its own function based on the win rate, right?
Mm-hmm.
That's what you're saying.
Yeah. I was just wondering if that's something that people do.
I'm not 100% sure if like that is, that's probably done. That makes sense. Sounds like it would work. Because like once you're more confident with your policies, with your exploitation, you don't want to explore as much.
Right.
But for something like evaluation, like when you're done training your net and you're trying to like see how it does at the end of training, like evaluate on the environment, you might decrease that exploration parameter because you want to just see how your policy is doing and not how well it does if it's doing some random states too.
Yeah, I think setting it to 0 in that case could make sense.
Mm-hmm. Okay, so it's kind of going through this. So this is we get our action only if this like we're doing a random action some percent of the time, and that's what I believe this. So yeah, that's what Leo and I were kind of just talking about, is we're doing a random action some percent of the time, and this is where we decide if it's going to be random or not. So this is where it's taking the random sample, and this is where it's taking from the Q table. So then we've decided our action in this part of the code. We have our gym environment, and each gym environment is going to have this step function. So we do environment.step with some action, and the action has been chosen up here. And we get our next state. We get our reward. We get whether the environment has finished, the agent has won or not. And info is a way that we just can keep track of other things that happen in the game, or like print statements that we want to, logs that we want to keep track of. And so this is where that updating is happening in the Q table based on the next state, the reward, and the learning rate. In this case, the learning rate is directly used in this update function. Like nowadays, instead of a Q table, you just use a CNN or some network, and you feed it the state, and the action. Actually, the networks, you just feed it the state. Or I guess you only do it. Sorry, you feed the network the state, and it gives you action probabilities from that state, and it gives you the expected value from that state, rather than using a table with state action pairs. Okay, so once we update our Q table, we can like increment our total rewards. In this game, I believe you only get a reward at the end, so the total reward is only going to be updated at the end. But then we set state equal to new state or next state. We break from this loop if the game is finished. This is where we scale down our exploration, and then we're going to start the loop over. This inner loop, rather. Sorry, right here. We're going to start the loop over and just keep playing that game, updating the Q states. After each episode, we restart the entire environment and start from the beginning. And then this code, it keeps track of our score over time, and it prints out our Q table. I can just run it now. I'm not sure. I don't think that, yeah, nothing in here would require like a GPU if you're looking to run it. You don't have that. So unfortunately, these are scaled like this, but this is just representing like if we start at an initial Q table, which is just all zeros, and we are updating that Q table over time. This is like how good each state action pair is for our agent. Okay. Oh, and in this, if you wanted to see each state, you see how it, so this is another play step, just using a Q table. And this is not updating the Q table, it's just, this is the evaluation step. And if we wanted to see each game step, we could include that there. And this runs 5 games. I'll just have it run 1 game for now. And maybe I could have it print the Q table after each game too. Okay, so what's going on here is I have it printing out the actions at each state, or the Q table at each state. So I'm pretty sure it's up, down, left, right would be these actions here. And it's saying it's moving down, down, down. Wait, but it's not moving down. Huh. I guess down is up for some reason in this situation. Or down would mean to the left. Sorry, that's very confusing. But it just moves through this, or no, I guess it's not.
A lot of the values look the same.
Yeah, because I think because we're at the same state in this case, right? With this pink representing.
Oh, I see.
So the actions at that state are going to be the same because they're coming from that Q matrix. See, in this case, we move left. But where is it moving left? I guess here and here is left. And then up, okay. Okay. So the actions are like, should be rotated. So up is going right. Very confusing, but I guess it makes sense. So up is the first one. So it has the highest value, so it goes up. Down must be the second one. So it goes down here. That doesn't make sense. Sorry.
No, these are looking kind of weird.
Yeah, this is me and Leo are like debugging. Okay, so Leo is my research partner, and this is us debugging like everything. Just like that doesn't look right. but yeah, feel free to play with this if you want to. It's been about an hour now, I guess. So I'll kind of wrap this up. If you guys have any questions or anything or whatever, thanks for coming.
Thank you for the presentation.
Of course, of course. Yeah, so AI at UCF has some other stuff going on. We've got some general body meetings and George. We got a lot going on if you're interested in that. I know clubs are so different this semester because everything's off campus, but yeah. Thanks so much for showing up, guys. I'll stop the recording.